So, welcome everyone. Today we have a very special guest. It's my father. He's also in the OE underwater acoustics mapping community. He was one of the original people here at CCOM when they all moved to me. I think he was in the same car as Larry, right? You all moved your furniture in together.
Exactly.
So, and he's back. He did a presentation a couple of years ago, but it was pandemic time, so it was over Zoom. So this time we got a chance to have him here in person. And I'm going to read off his bio. So Professor Luciano Fonseca has a PhD in ocean engineering at UNH, a master's degree in electrical engineering at the State University of Impedance, Unicamp, and a bachelor's degree in electrical engineering from the University of Brasília. He's associate professor in electronic engineering at the University of Brasília from 2012 to present, and a member and consultant of the Brazilian Leplac UNCLOS program, or the Brazilian UNCLOS. He was a visiting professor in underwater acoustics at the IFCAMER, if you know it. Xavier, also a guest here this week. He was specialist in the marine geophysics programs of the United Nations Intergovernmental Oceanographic Commission, IOC, in Paris. He was associate professor at UNH at CCOM from 2002 through 2009. And he was a research geophysicist at the research center of the Brazilian oil company, Petrobras, in Rio de Janeiro. His main lines of research include underwater acoustics, marine geophysics, remote sensing, marine GIS, and scientific visualization of oceanographic data, ocean sciences, and geoengineering. So please welcome our guest.
So I'm very glad I'm here. Thanks for inviting me for the seminar. It was an honor to me to be here. And I was trying hard to find something interesting to show. That was it was a paper that I published in Marine Geophysical Research. And it's actually a problem that I had. I had the data, I had to process it. So I could not extract anything from it. I said, I have to find a way of getting around it. So I'm gonna share with you guys the results that I had. And what amazed me, that's why I decided to publish it, because I started using it all data sets that I was getting from the Navy in Brazil, from the CPRM with our geological service there. And the theme is restoration of multi-beam records. Okay, so probably sounds familiar to you. Data set that was acquired for bathymetry. They do not care at all for the multi-beam. And suddenly they decide to extract some information from it. Okay, and so I call it restoration, not enhancement. So I want to make it a clear difference for me, at least, you know. So restoration aims at recovering, you know, the original data slash signals. You know, I would like to remove some degradation, some noise that added to the data. You know, enhancement, you don't aim to restore, you aim to enhance, you know, the way you're gonna interpret the data or emphasize special features and so on. And I think I have, and use this to change the, okay, good. So this data set that I'm gonna show you guys was acquired in Admiralty Bay. It's a station that the Brazilian Navy has in King George Island, next to the Antarctica Peninsula. There are many stations there. No? Okay, sorry. There are many international stations there. The Brazilian one is here, next to the peninsula. And it was a study based on movement of glaciers and dating glaciers and so on. And they use a multi-beam, 30 kilohertz, and water depths from 100 to 600 meters in the bay here. And We actually acquired many piston cores there. It was a very good analysis of the piston cores. Well, the problem is that the backscatter was horrible, in all the sense, this is the best we could do. And you see there are many motion artifacts. And it's not only a problem of appearance to the mosaic. If you try to analyze the statistics of the backscatter, if you try to analyze the angular response, all that noise went through the data, contaminated the data, contaminated the statistics, and there's nothing we could do to get it better. You can average out, but it will not help too much. And so that's more or less what was being done. I'm gonna show you. And it's basically the way we assemble backscatter mosaics. You can get a waterfall of data. You see each acquisition, each line in the waterfall is one ping of the sonar. And we can first assemble this waterfall. So this is the angular response. Each line of the waterfall is one angular response. And then the final stage is the mapping. So the mapping, in the waterfall, we do not have the navigation. We only have like ping number. So the line here, the line number is a ping number. But in the cross-track direction, can use time or can use distance, depending on your goal. And then when you map, you include the vessel movements and the navigation. You can assemble the final mosaic in map projection coordinates. And you can see clearly how the artifacts, all the noise, went through the data and contaminated the data. I tried a lot to remove the artifacts with the tricks that I had. Changing offsets, delays, filtering, smoothing, the heading, smoothing this. It did not work. There was no way I could remove it. So I said, can I try something in the frequency domain? Well, I did not know if you guys had like courses in signal and processing, the signal and systems. I teach signal and systems, so for me I'll put a couple of slides there to explain what I want. If you have a single tone, a single frequency. If you take the Fourier transform, this is actually the Fourier series, but you can use the Fourier transform. If you take the Fourier transform, you're gonna get two tones here. One at the frequency, the other one is in the negative value of the frequency. And the energy here, so if you have amplitude here 10, you're gonna have amplitude 5 here. If you have a combination of tones here, I actually made this signal, so I know the frequencies it has. So it has frequency W0 and 3 times W0. And the transform gives me exactly the frequencies that it found in the data. And preserving the amplitudes. It's a very easy tool. It's not difficult at all. And here we have 3 tones, and they are there. Well, this is what you get in a signal processing book, But when you analyze the real data, It has all the frequencies, you know. I've never seen a data that had a sinus and a cosinus there. Yeah, it does not have. So, for instance, this is a way, or I'm struggling with this one. I have this whale whistle here. I took the Fourier transform. You can clearly see it has some tones, you know. That's why they call whistle, you know, because you can clearly see there's one frequency here that dominates, you know, here around 500 hertz, you know. There's something at 600 here. Actually, I separated tones here. So it's a nice tool. Here I got a dolphin. A dolphin, they do not call whistle. They call clicks. Sometimes Portuguese they say they barks. You know, actually clicks and barks. You know, it does both. I can play the sound here if you guys want. Let's see if I have if you can see the Fourier transform. And let's see if it works here. This is the way, huh? So it has a clear tones, I like it. So it's good to see what we expect when you have clear tones, you know. When you see the Fourier transform, you see very well-defined bars there, what you expect in the signal. And when you have something like that, clicking, you know. So when you click, you always have high frequencies, you know, and it's spread all over the field. So so what, coming back here, what does it help with our orientado paper? So if we get now a 2D Fourier transform, we're dealing with an image now. So if you look here, so here would be time, okay? And here's frequency, and you have the energy, okay? Here, we're gonna have the same thing, but in 2D, we have X, Y, and the energy is the gray level, okay? And so this frequency here is related to like a sinus wave, you know? I have these two energy centers here and there. If I spread the energy here, I increase the frequency. If I spread a little bit more, if I get them in the X direction, I get the same pattern. And I have, with an angle, a pattern too. So this is, you can use this as an interpretation clue, you know, what you expect. So if I look at the waterfall here, it's clear that I have some energy in this direction here. So clearly that energy here is contaminating the signal. So if I try to apply the filter in the map, okay, in map coordinates, so things gonna spread like that. So it's impossible to remove. Here's very easy to remove. I can put a filter that are gonna remove energy in that direction. So that's why we decided to apply the filter. We call the waterfall notch filter. It's not the mosaic notch filter. It's a waterfall notch filter. So that's how it works. And so we had the idea, but in order to make it work, sometimes you need to tweak a little bit the tricks. If you remove all the energy, okay, along track, you destroy the DC level of the signal. You're gonna lose the average of the signal, the sea level. So you need somehow to stop. You cannot remove the low frequencies here. So which low frequency to remove? That's a scientific question, you know. So you can see, I assume that the artifacts are coming from the motion sensor. So the motion sensor somehow did not read, or was reading wrong. So what's the lowest frequency that the motion sensor can record? So it was like I think that the longest period was 60 seconds, you know, that you could get. So I got 1 hertz. So we cut it here, but be careful, we have to use normalized digital frequencies. We're in the digital, so just be careful when you choose the frequencies. So that's it. So what I'm gonna do, I'm gonna remove I'm gonna preserve the central edge here and remove that energy here. It's clear to me this is an artifact. There's a second way, it's a very effective way of finding the limits of a notch filter. It works pretty well too. You can use the motion sensor if you want, or you can take the 1D Fourier transform, okay, one-dimensional Fourier transform of the columns. You collapse of the columns of actually I should have turned around the map, and you see here that you have some energy here that should be removed. No, it's a very effective way too of finding the limits of the filter. And so that's the result. It's a very promising result, and this is the original waterfall. So I filtered the waterfall, just applied that notch filter, and this is the difference. By evaluating the difference, we see that basically remove just artifacts. A little bit of signal somehow, because you go through here, but it's basically you remove artifacts. And this is the result of, now I filtered the waterfall. This is then I map, and I sent to map coordinate systems. And so this is the original map, and this is the filtered map with a notch filter. So after now assembling a mosaic, the geocoder way, assembling the mosaic. This was the original one with the noise, and this one is the corrected one. So this is a huge mosaic, so I have to put a zoom area here so the guys can see the difference. Well, but so a nice mosaic, okay, that restored records is one side of the story. The other side is actually when you deal with waterfalls, you retain, the acquisition geometry. So it's very easy to see. If you look in one line of the waterfall here, you can take an angle. So we did not lose. So you have a map, okay, from beam to the waterfall. So if I apply a correction to the waterfall, I can backtrack that correction to the beam, okay, to the beam. So I can actually correct the angular response using the same result that I got from the notch filter. So that's for me was fantastic, because the angular response were all contaminated with that noise. So we we did the angular response analysis. It was possible to do angular response analysis and compare to ground truth. Actually, we had a wonderful ground truth. You know, for all the piston cores, we had like that. We analyzed that with a multi-sensor core logger, and so we could get a profile of impedance. So we could start thinking, oh well, the acoustics gonna see what, like 10 centimeters in the sediment, 20, 50, you know, what would be the penetration of the acoustic wavefront in that sediment? You know, I can look in a table, see attenuation, you know, dBs per meter, and try. So our guess, our best educated guess was that we could get like an average of the top 50 centimeters there was a soft sediment, and assuming that that would be the maximum penetration we will get in the sediments. But this is an interesting question. You know, sometimes we talk about the impedance. Well, the impedance of the top 5 centimeters, top 10 centimeters, top 50 centimeters. You know, when we have a profile like that, those questions arrive. But anyway, we could only start thinking about angular responses and comparing angular responses to actual field measurements after doing the restoration. And another wonderful source of data was that Le Plaque project. This is the mapping program for the extension of the continental shelf. You know, you see, they use multibeam to map the foot of the slope. They don't care at all for backscatter. And that data was lost there. So I tried to restore it, recover it. So I got all the records. You know, since I was part of the commission, I had access to the data. So I got the data. You know, you see, the whole Brazilian coast was covered. You know, very sparse lines, aiming to map the foot of the slope. Actually, they use EM1 to 2 at 12 kilohertz for the deeper sites, okay? And when we go to the shelf, they use the 710, 90 kilohertz. So basically, those were the maps that were given to the commission, and I basically could not see anything, you know. So maybe it's a question of stretching the histogram, or that was the first thing I did, you know. And so I just stretched the histogram, okay. I took exactly this line here, see? I just stretched the histogram. And what I actually got was, a grayer version of the image. There's no information at all there, no, see, and so they use that side scan color table. You know, low is white, high is black. You know, I don't care too much, but you see that basically there are so many samples in low that the histogram was completely lost. Okay, so I finally got the original records. Okay, and I just put in the code. You know, I did not write any new code to process multibeam. I just dragged the file, and that's what I got. You know, then I understood why they did that stretching. Okay, they did that to hide. You know, because this was so horrible, they could not show that. You know, they stretched out. So basically, it's hard to tell which one is worse, you know? 'Cause this one, at least you try to see something. And then I just applied the notch filter, the miracle notch filter. I swear to use. It's like a kind of spell, for this kind of things. They were all restored here. I just left this one the way it was for you guys to see the difference. Well, and that line that you could not see anything, that one here. After the notch filter, you got this. You can see those nice formations there. You could do your interpretation. I was very happy with this. So simple. The signal. It's a band pass filter. Just I learned this. So I just going over all the. I do not put the name. I removed the name of the company here. Put deliverable. Be nice with them. I'm not, if someone wants to know, I will. And this is the reprocessed backscatter. So we use for many things, and this one I like a lot. This one because in water depths between like 500 and 200, they kept both sonars running. So I had two frequencies, so I could actually start using backscatter into different frequencies, making color composites, things that were possible after restoring the data. So I have here the angular responses at 12 kilohertz, at 90, in all the sites. So this is an area that ended up being very important, because Petrobras, the Brazilian oil company, wanted to explore oil offshore the mouth of the Amazon River. And there are many environmental concerns there, and then they did not have any data at all, and they wanted to know areas with rhodolites, because rhodolites, they have to avoid them. It's something that I tell. So in many situations, oil companies and wind farm, the wind farm industry, they are not interested in mapping the environment. They are interested in avoiding the environment, anything. So it's the opposite. But anyway, that data was extremely valuable. With a couple of lines, they could trace out one area that we're planning to go there. And that area was completely avoided just by reprocessing that data. It was very useful, We could also use the statistics that we've been discussing, to make a histogram of all the acoustic samples in one certain angular range, depending on what you're looking for. and this is a technique that I use at the same place. So you have the histogram of measurements there, and you compare to a fitted distribution. And actually, you see that in some places the distribution does not fit properly the data, and you associate that to the presence of the rhodolites, which are high amplitude scatters. So the high amplitude scatters would add energy here in the tail of the distribution. And when we fitted the distribution, that variable distribution, it was dominated by the substrate here. So it's dominated by the substrate, not by the scatters. And so this was one part of the presentation. This one here is quicker, I promise you guys. So the next part is the mapping. Okay, it's actually when we get from the waterfall to the map coordinate systems. And so the way we assemble the waterfalls and then we warp the waterfalls. So see, not warp, we map line by line the waterfalls. Let me, I think this slide here shows it perfectly. So basically each line here we put and we interpolate. So it's like all the softwares that do something like this. They kind of move with, they take the vessel coordinate system, the navigation, the vessel attitude, and they project the beams on the seafloor, and they start doing the interpolation. Now, this is the way it's been done since people were making maps with side scan. You see, but that kind of mapping, we all know, do not work pretty well in turns, you know. When the vessel is turning, you know, you see like this, you see artifacts like that, you know. I saw that John Hughes Clark was showing that donut shape. I was thinking about mosaic in that donut shape. So it will be full of artifacts like that. No, you cannot avoid it. You can, and if you smooth the heading, it gets even worse. You know, there's nothing you can do, and so it happens. Well, mainly in deep water, we always see that. Not even in curves, but in something when you have like a low density of acoustic samples, you have problems with the mosaic. So we try something different. Okay, let's try something different. So because when we map, we see all sorts of motion artifacts. But when you look at the waterfall, they always look fantastic, you know. Did you have this impression? I have this impression. Look at the waterfall, you see it's perfect, you know. But when I see the map, it does not follow the waterfall. So I say, wow, what if we can warp the waterfall? I'll do a map in deep water the different way. So I get some control points, because I have control points, just like we are warping and mapping an aerial photograph. Okay, and of course there are some geometric problems. There's some topological problems. No, basically you get a set of control points. You choose the number of control points that you want, and then you warp, you distort and you get a perfect shape there. Exactly what we were expecting, you know, we were dreaming about. And so it worked pretty well. We implemented actually what was one of our master students. We implemented the notch filter and the waterfall in a plugin in QGIS. I think this is very cool. You can program in Python, and you can use all the interface for displaying and so on. So it's actually working in Python here. And there are huge problems. It seems easy, you know, it seems easy, but you can have some instabilities. No, you see, if you have, I said, you need to put some topological constraints, and it's not 100% solved this problem. No, probably needs some help, but we just using a convex hull, see, so I'm moving every time I add a control point. That control point cannot get inside the convex hull, otherwise there's a topological problem, things like that, and it converges. So it's a geometric topological discussion, and you can search the waterfall to see if you have double features, very easy, and you can collapse those points. Some easy algorithms that help with this waterfall warp. It's a different way of. So I applied that in the middle of Atlantic there, in the area called Rio Grande Rise. The data was very difficult to work, and see all those maps here were assembled with this called waterfall warping technique. And you see when you have the shoulder here, the curve, it looks nice. It does not look like jumpy or coming back and painting the data again. Things that we see even in extreme cases, that data is very shallow water. I do not know why they went there with that sonar. It was not supposed to go there, and maybe they were testing the limits of it. So it was the record was horrible. There was nothing there. But with the two techniques, well, it's there. You can see, and. This is a huge mosaic, from data that I got from CPRM, the Brazilian Geological Service. They went there. This is the Rio Grande Rise that I was talking about. So the whole mosaic here is EM201, 12 kilohertz. It was all assembled with that plugin using the waterfall warping technique. So some simple conclusions that I can share with you guys. I would say that Multibeam data, even when collected primarily for bathymetry, well, basically it's all 99% of the cases, and with no care, contain variable backscatter that we can recover. Our restored backscatter records enables new applications like habitat mapping, geological mapping, environmental assessment, things that they did not think about when they collect the data. And the recovery process demonstrates that legacy data sets have untapped potential beyond their original purpose. It's a logical conclusion, but sometimes we forget. And the restoration process, it's very simple, that we apply all the radiometric and geometric corrections to the backscatter, of course, follow all the rules, and then we assemble the waterfall image. We apply the filter, the notch filter to the waterfall image, and then we feed back the notch filter results to the beam backscatter. This is very important, recovering the acquisition geometry, and then we can do the geometric warping, pattern map representation, do statistical analysis or angular response analysis. So the notch filter that I used was a simple one. Okay, reduced the artifacts by 40 dBs and did not change the statistical moments of the data, the average, the certain deviation. And let's see, that worked for my case here, but with careful analysis, most part of the motion artifacts can be isolated and removed in frequency domain. So if you look carefully, you can find it. using those, that map that I gave you. And this is, well, a call for help. Additional topological constraints and more careful selection of control points can improve considerably the warping process, see, and it can be extremely effective. Well, that was it. I think I got my
time. Open it now for questions. Any questions? Yeah, 10-second question. Yeah, or Tom?
Oh, sure, thank you, yeah, I appreciate that, yeah. Signal processing was awesome.
Oh.
Have some of these guys who took my class, so.
Okay, so
So the, how did you determine the cutoff for that low frequency notch filter?
you
So
see,
there's science involved in that, is it based on the artifacts or the data that you're looking at?
you see, well, the high frequency, we're talking notch filter, it's a band pass filter, has a low pass and a high pass, okay? Well, the low limit, we try to preserve as much as we could. And so I looked at the motion sensor. I said, what is the lowest frequency that the motion sensor can track? Okay? And that lowest frequency gave me the lower limit of the notch filter. But I'm going to erase everything that the motion sensor read in that direction. And the high limit, okay, there are two techniques. I could just remove everything to the end. It's just noise beyond, okay? Just remove from that. Let me show here, otherwise it'll be, look, okay, here. So that delta, the lower limit, is given by the motion sensor. Okay, and the high limit, I remove everything. Okay, it do not change too much. But if you want to be pragmatic, you can get the 1D Fourier transform. You can see that limit and remove and choose the frequencies. It's both techniques work.
Can this same filter be applied to bathymetry data as well as the backscatter?
Well,
Would it be a useful tool to help get rid of artifacts and make them?
yeah. I haven't thought of it, but see, if we get the bathymetric grid as an image, we can track those artifacts there. Okay, there will be different frequencies involved.
Each ping,
Yeah.
as you move along the track, can be interrogated for depth, independent of the.
Yeah, you see, I will have to test, because you see, that lower frequency is a key there.
Yeah.
Because I see, well, I'm going to remove everything until the lowest frequency that the motion sensor gets. Maybe that frequency for bathymetry, it's too high, For backscatter was okay, All the main features of the backscatter, the long track, were preserved by removing it. But maybe the bathymetric features have lower spatial frequencies, and maybe you can remove more things there. I don't know. But I'll probably test it. I think it's a good idea.
I have a follow-up question, but I'll let somebody else.
That was actually almost exactly my question, but in terms of your answer, could you clarify a bit more how the upper limit of the filter was chosen?
Oh, see, the upper limit. I'm going to show you this other feature here. Let's see if I find it. Oh, this one here. This is very, instead of taking 2D Fourier transform, you know, I just collapse all the columns and I took the Fourier transform of the columns. And I see that there's some energy here that, well, it's strange, you know. It looks like it's exactly in the band of the artifact. So this is what we have to remove. So I can build the filter, the notch filter, beginning here and ending here. So that's basically can do that. So the lower limit you can use here. So if you do not want to do that, okay, if you want to just base on the, because in order to do that, you need to open the data and analyze. But if you want to do a batch processing, you can just open the multibeam record. You know the motion sensor that was used. You can tap the lowest frequency that the motion sensor is going to get. And remove everything, you know? You can remove everything. Remember that you're not removing all the frequencies, you know, only the frequencies from the lower limit to the high limit in that tiny direction, the long track direction, which is very well defined here in the waterfall. If you did that same filter in map, you had to remove a lot of things. So you're going to blur the data. Okay. And there's a small detail that is, when you assemble your notch filter, you need to put a tiny gain in the pass band in order to preserve the average of the data. You know? So it's a small detail, but okay, put a .1 dB gain in the pass band. So it's a balance between what are you removing, what are you preserving, you know. So it's a small trick from electronics. You do that, you know. So I love it.
I have a question and a comment. I'll just make the comment briefly. You're talking about doing this with bathymetry, and of course, you have to have a very particular kind of problem in bathymetry. And we have it sometimes with a heave artifact or in an underwater vehicle when an underwater, like an AUV, is operating in shallow water and it feels the motion of the surface and the pressure sensor, it imparts what looks like a movement to the vehicle that's not real, and so it produces a heave artifact, and we solve it with a filter very similar to this.
Fantastic.
My question was, what do you think is causing this banding?
Well, see, I swear to you, I was not able to find.
Did you get recordings of the motion sensors? Normally they are logged with the multibeam data. Was not something to be identified in them?
Yeah, I see. I saw huge delays. It was not consistent. You know, I have tools that I take the waterfall and I plot the heave, the pitch, the yaw, you know, and so they look random to me, you know, I swear to you.
Very curious.
I could not solve with, I could not solve with the tricks I had. And I tried, you know, what you're telling, you know, see, the first thing I did, you know, plot, this is the problem with the, you know, it's the pitch. It looks like pitch to me. Yeah, no.
What does it look like in the bathymetry?
Well, the bathymetry, it's okay. Definitely okay. You do not see that in the bathymetry.
I mean, it's just remarkable that you'd have a motion-induced artifact, or maybe a motion sensor-induced artifact that doesn't show up in the bathymetry.
Yeah. In the mosaics that I did, I could not identify. Maybe it's a frequency that did not go to the bathymetry as he asked, you know. It was a frequency that passed to the backscatter.
If you have bubble, some sort of
Could be,
insinuation.
this is one
It's still a
hypothesis.
signal, but it would just cause a drop.
Could be, it's a very good waterfall, it's could be bubbles.
The question about your angle. You make it look like it's a variable, but I have a suspicion that you're probably not changing that. Is that-
You mean the angle?
You've got that
Theta.
Oh, okay. That angle there, no, you see, well, I want to make a simple filter, okay, with polar coordinates. And the most logical way was to use an angle, not to remove one row of data, no, I want to, because I do not want to remove a lot in the center. I would like to remove more, okay, because the uncertainty will go higher when I get, okay, in the higher frequencies. So I would remove more in the higher frequencies. So I chose an angle, okay, and that angle looked pretty well. And and I use that angle with the maximum yaw that we're recording in the.
Did you compare this with your next plot where you just used a 1D?
So the next one, which one?
You showed where you collapsed the waterfall. Yeah. Did you compare those two?
Yeah,
And they similar?
they basically the same. And but that angle I said, you see, if I have an uncertainty in the yaw, okay, when I'm moving, okay, so I propagated that that angle there. I put the maximum angle uncertainty that in the motion sensor.
Can I ask a question?
Okay.
It's maybe something that would take a long time to answer in detail. So your filtering methods are linear. I'm not convinced your artifacts always are. Some of your artifacts are dropouts, they look like clicks. So they're going to be a non-linear change in the signal. And I think you can see it in, I think one of the very first examples you saw, the cleaned up version is dramatically cleaned up. But you can see where there's been a click across the swath, and it kind of is blurred out on both sides, which is kind of what you'd expect. Have you considered using something that might adapt to that? Some like, detecting where it goes nonlinear and ignoring it, or maybe doing something that wasn't global, like a wavelet decomposition and denoising the wavelet decomposition? Does that make sense in your opinion? It's a lot more complex, obviously, but would that make sense? Do you think it's worthwhile even pursuing?
Well, I think definitely is the way to go, because see, I'm assuming here that the frequency content and that the waterfall is the same, okay? But we can make a short time Fourier transform, 2D Fourier transform, like a moving average, See, so I assume that the frequency content here does not have to be the same as there, See, I think it can be a definitely improvement there, definitely. And probably we can track this short time variations, we see. Could be wavelets or gonna be a short time Fourier transform.
What I was thinking of is if you had like a click detector that detected when you had something that was unlikely to be filtered well by this, and then you could just drop it from consideration and do something else.
Yeah,
you don't try and go fully non-linear, but you sort of drop out the bits that are, and then and then patch
we can track the spectrum if you see that something suddenly happens in a change that happens in all the frequencies to be a click. Okay, a click we're going to spread through the spectrum. We'll be not constrained in that. But I think that the short time Fourier transform could be something to improve it, definitely.
We're over. Oh, yeah, okay, that's enough question. Well, thank you.